Hmm. Oh, okay. There you go. Good. Okay. So that's my question. Does anybody have an answer? So basically, when we discussed last week about atomic representations, where you think in terms of black box states and actions um, mapping from states to states, right? We talked about this before. Um, so, and then we then went into lifted representation of actions, with the strips representation, and okay, strips representation. And we also basically found that, and I made some arguments as to how strips representation can be smaller than the action representations. The question is it always going to be smaller, or sometimes it may not be smaller at all? Why not? Always specify all the preconditions. So to make things simple, let's assume the following thing. Let's assume the following thing, that to compare oranges to oranges, right? Let's assume that the world is completely describable in terms of n Boolean fluents. Okay, so that's the world. Whether you actually think in terms of atomic states or in terms of basically propositional states, the world itself is indeed completely describable in n Boolean Boolean propositions, Boolean state variables. This is important because this guy was saying he was going towards the whole direction of what has actually been called qualification and ramification problems in real world. What is a qualification? What's the qualification problem? The qualification problem basically says that in a real world scenario, you will never be able to write all the preconditions of an action. You can't ever fully qualify. There'll always be some preconditions you have forgotten. And similarly, in the real world, real world, okay, there can be ramification problem. Ramification problem basically says you would have forgotten to say some of the effects of the action. Do you understand what I'm saying? Okay. The example of qualification problem brings us to another of those beautiful things. Remember, we talked about bomb in the toilet? How many people remember bomb in the toilet problem? It's very important, right? Basically, you should know why you care about bomb in the toilet. It's basically showing that you can actually achieve goals even if you can't sense the state. That's very interesting. Okay, a variation, a different problem, just equally colorful, is potato in the tailpipe. Problem. Okay, potato in the tailpipe problem actually was due to this one guy called John McCarthy. Has anybody heard of the name John McCarthy? So the name artificial intelligence was given by the guy John McCarthy. You're taking courses and you are trying to get jobs in an area which was named by this professor called John McCarthy, right? And he essentially named the area artificial intelligence. And in 1956, there was a workshop, Dartmouth workshop, and he was one of the people who proposed the workshop. And he decided to call the new field artificial intelligence rather than cybernetics. How many of you have heard of Norbert Wiener, the name Norbert Wiener? How many of you heard of anything other than just the current pop stars' names? You should know a little more than just the pop stars' names. Norbert Wiener actually was looking at some of the many issues that are important for artificial intelligence. And he was looking at it from the perspective of what he would call cybernetics. His area was called cybernetics. In fact, the word cyber comes from that direction. So he actually, he was not the guy who named it that way, but cybernetics was the field that he was looking at. And the apocryphal story is that John McCarthy couldn't stand Norbert Wiener. But he was going to do the exact same thing that Norbert Wiener was going to do, but he couldn't stand Norbert Wiener. So he said, anything but cybernetics is going to be the name of the field I'm going to start. And so he decided artificial intelligence. which is a questionable name. You can make lots and lots of problems. Like our own school calls itself School of Computing and Augmented Intelligence, but nobody cares. I just write my papers as School of Computing and AI, and let's assume what people assume. Right? Does anybody, you can't make fetch happen, right? For those of you who understand fetch, how many of you understand the fetch reference? You can't make fetch happen. When were you born? Yesterday, day before, when? What's going on? So look up all these references, okay? You can't make fetch happen. And so you can't re-change the name of AI to be something else other than what AI is. It's a weirdo name, but that's what we got stuck with. Okay, so anyway, now John McCarthy was the guy who actually also came up with the idea of the example of potato in the tailpipe. What is potato in the tailpipe saying? Which it's basically asking you, give me all the preconditions that you need to check before if you're about to start the car. So there's an action called start the car action. And its effect would be the car will start. Right, as we defined. So the question is, tell me all the preconditions. Obviously, all the preconditions that need to hold. So you will say, well, yeah, I need to have the car, and the car. I need to have the key, and I need to be able to get into the car. I need to be able to start the car. Turn the key. Blah blah blah. You write a whole bunch of things. And then after you write, then I say, are you sure? You'll write some more. Are you sure? You'll write some more. Are you sure? You'll write some more. You will basically, at some point of time, you'll start saying things like, and there should be an engine in the car. Because, you'll still say, are you sure? And you say, oh, there should be, none of the wires should have been cut off. Then I'll say, are you still sure? You'll keep on going like this. And at some point, I'm like, okay, I'm done. I've written like about 10,000 preconditions. I'm done. Then I'll say, what if there was somebody put a potato in the tailpipe? This is only for the pre-Tesla people, right? For those of you who understand how internal combustion engines thing work, if you put like a potato in the tailpipe of a exhaust pipe, then the car will sputter and die. So that should give you a thing that in any real world, you can never, ever write all possible preconditions. You're always thinking in perspective model of the world, because there is no such thing as actually modeling the real world unless the real world is a video game, in which case, of course, you can model because you wrote the video game. Real world cannot be modeled. That's why, with all the great NASA planning, you had Apollo 13 happen, or O-ring happen, or Challenger disaster happen. After that, you say, oh, we should make sure that the O-rings will not be used in that way. But why did you think about it before? Well, there are like a gazillion things you could think of. You thought of enough number of things, and you ensured that there was some reasonable robustness, and you hope for the best. That's pretty much what Boeing is doing too. That's why it's actually, as much as all of us hate liars, I don't know, I should say all of you might be hating liars. Liars are important, because when things go wrong, there better be an actual fine so that next time around you won't make the same mistake. Civilizationally, the only thing we can hope for is we won't make the same mistake again and again and again and again. Do you understand what I'm saying? Okay, so that's about potato in the tailpipe, and that's because that tells you that you can't write all the preconditions, you can't write all the effects. And I think, I don't even know that whether you are thinking at this level, but I was just, once somebody could say, well, you could just, if it's a black box state, God knows what all the description of that state, and maybe you could write things that, you could say things in that model that may actually take larger number of preconditions and effects in the other model. In the lifted model. So I will change the thing and say, imagine that everything is the same, that basically you are only trying to model a simulated world, which can be completely described in terms of n Boolean variables, n Boolean state variables. At that point, can you see whether Strip's action representation would always be more compact than the atomic representation? Do you understand what I'm saying? It's a very complex question, actually. Most people don't know how to answer this. Even if I ask in the planning, conference, most people haven't thought about it clearly enough. Yes.
If we do an atomic representation, it will be like, for every combination of the state variables, we need to find what will be the result for an action, which is like, I think, n by n.
Yeah, it's always going to be n by n. So, I mean, you can look at it as a bug or a feature. The good thing about the atomic representation is it's always going to be n by n.
For splits, I think it'll be a bit more compact because you could use conditional probability.
No, we didn't even talk about probabilities yet. We didn't even talk about probabilities yet. We can get there, soon enough, but we haven't gotten there yet. It's all deterministic right now. Right? So the question basically here is, you can see that there are 2 power n states. The state space is 2 power n. You'd agree. And so in the atomic representation, it'll always be an n by n matrix. Always. I'm sorry, 2 power n by 2 power n matrix. 2 power n by 2 power n matrix. Agreed. Whereas a strips representation, your hope is that the action will say precondition, and it will mention some subset of state variables and their values. So it means this state variable should have this value, this state variable should have this value, this other state variable should have this other value. Right? And then fx should basically be telling us exactly what variables will have what values. SV1, SV7 will be true, SV9 would be false, and everything else remains the same. This is what you think of as strips representation. Do you see what I'm saying? But this kind of good thing will happen if you have actions that essentially have non-conditional or unconditional effects. That means if the precondition is holding, it'll just give you one set of effects. Do you see what I'm saying? What the heck are you doing? This guy is a PhD. I don't know why he's sitting here. So you have basically 2 power. Non-conditional effects. If you have non-conditional effects, then you are happy. But many times the actions can have very highly conditional effects. Highly conditional effects. An example of a conditional effect, is here. This is a strips representation of one-way rocket domain. This is a strips representation of one-way rocket domain. Okay? And it's a very, very simple domain. It basically is trying to send stuff from Earth to Moon, and there's some packages. Okay? So I will, there's an action called load, which basically, you load O1 if in fact both the rocket and the package are in the same location, then you can load it into the rocket. That's what it's saying. Unload is the same one. If it is inside the rocket, it would be not inside the rocket. But where will it be? Well, wherever the rocket is. Do you understand what I'm saying? Okay, and then comes fly action. Flying action, the real precondition of flying action is that the rocket is on Earth. And the real unconditional effect of flying action is that rocket will be on Moon because it's a one-way rocket. But it has a whole bunch of conditional effects. All the packages that are inside the rocket will now be on the Moon. Do you understand what I'm saying? For example, what is the precondition for an American Airlines flight to take off? There's a pilot, there's there's basically enough fuel, all that stuff. Is there a precondition that you should be in your flight before your flight takes off? No, that's your problem. The plane will take off. And if you happen to be in the plane before it took off, after it landed, you would be in the other place. Otherwise, you'll be happily in Tempe. That's a conditional effect. And it's a very reasonable kind of effects to talk about. Right? And so, in general, in some complex enough situations, there can be many, many conditional effects, making the action description larger and larger, or there would be too many different kinds of actions. Do you understand what I'm saying? Whereas atomic action representation will never increase. It's the same n by n. What this actually means really is that the strips representation is useful. In fact, this is sort of true for many representations we live with. This is more compact only if actions have localized effects on state variables. That's actually a way of thinking about it. When you do an action, it only changes a few state variables and pretty much unconditionally. Amazing thing to do with strips representation. Right? If not, eventually you will keep adding all these other conditional stuff, et cetera, et cetera. These actions will start looking ugly too. Pretty much the only reason real world domains the domains that you care about, when you model them, they tend to have compact representation in this lifted representation, is because actions tend to have localized effects. How many of you heard of butterfly effect? Would you like to live in a world where butterfly effect is very much possible anytime? Because that's the reality, right? Butterfly effect essentially is that a butterfly flapping its wings can actually cause avalanches or make storms happen in some other parts of the world. Everything is connected to everything in a real world with low probabilities. But most of the time when butterfly flaps its wings, nobody cares. Most of the time we can get by ignoring all those things, because of which actually you can have localized effects. When people talk about structure of the world, let's exploit the structure of the world. This is sort of what they have in mind, that the actions can essentially be having localized effects, allowing you to write them in compact fashions. If not, you with your small brain wouldn't have actually survived in this world. Do you see what I'm saying? So that is actually the answer for that question. I didn't really expect anybody to know it, but I think you need to understand why, when are actually lifted representations are going to be helpful and when they are not. They're most of the time helpful, but you have to realize that when things become very conditional, then there would be a problem. There would be a problem. Okay, so before going forward, any questions? Any other questions you have? Okay, so then we looked at this description, right, for a one-way rocket domain. It's even simpler than Bloch's whole domain, it turns out. The only strange thing is it does have this conditional effect. Okay, by the way, this one is called conditional effect. And in the case of conditional effect, one weird thing is, okay, so here is another thing. Okay, normal strips actions can't have disjunctive effects. Do you understand what I'm saying? You can't have a strips action which says if you do action O1, then either P or Q would be true afterwards. That's not deterministic. Do people understand that? If you start having PRQ, then you are actually talking about stochastic actions. And then if you start saying P with 0.7, Q with 0.3, then it becomes, actually, when you just start having PRQ, then you're having non-deterministic actions. And if you say P 0.7, Q 0.3, then you are saying stochastic actions. Do people understand this? Right? This is basically what you are hoping for, the probabilistic listing, etc. So in the deterministic case, obviously, strips doesn't allow disjunctive effects. Okay. Now, how many of you know that if I say P implies Q, there is a way of writing it without implication sign, right? What is it? Not PRQ. I said two things that seem to basically be inconsistent with what I just said here. Right? Like, because it says in X implies at XM and not at XE. And if it's a real implication, then I should be able to negate that and disjunction of that with other things. You should care about these. This is how you figure out how things are truly connected. You should see surface level mismatches and then see why doesn't the world end even though there is a surface level mismatch. Can people figure out why it is actually the case that even though there's this kind of an implication, it's not a disjunctive effect? Come on. Why is it not a disjunctive effect? The word English if doesn't necessarily mean that the antecedent and the consequent are in the same situation. Right? If you are in the flight before it took off, then you will be in San Francisco when the flight lands in San Francisco. So the disjunction will then become either you are not in the flight when it took off, or you will be in San Francisco when it lands. There's nothing wrong with that. The only problem would be either you are in San Francisco or not in San Francisco. That would be disjunction. Do you understand what I'm saying? So the way to think about this is the antecedents of a conditional effect are about previous state. And this is about next state. Do people see this? That is why this implication and that implication, this is actually syntactic sugar. It's not real logical implication. Well, actually, it can be written as a real logical implication the moment you start writing what's called the situation arguments. That is, in X is true in the previous situation, then at X on the moon will be true in the next situation. And we are sort of ignoring the situations, basically. In fact, there is a whole entire discussion we can have about providing strips. Strips turns out to be a simplification of what's called, what actually McCarthy called situation calculus. And for the situation calculus, you actually write in the normal logic. You don't need to have strips representation. You don't need to come up with new representations. Okay, but it turns out that situation calculus has its own issues. We don't talk about it. I can give you a link if people remind me as to what would be the problem. It's actually a better way to do planning, but it's like the first principles way to do planning, logically speaking. But if you can make certain assumptions, strips representations are actually much simpler. Okay, so that's the representation for the one-way rocket domain. Are you happy with this? And the one other new thing you learned now is, in addition to the preconditions and effects, you can have conditional effects. And one of the other things you realize is that I don't any longer talk in this representation. I don't, in the original representation, I talked about add and delete lists. That's the normal strips representation. You say add and delete. Add basically means make the proposition true. Delete means make the proposition false. This is one of those crazy, it's like, right is better than left kind of conventions. Up is better than down, north is better than south, all these nonsensical conventions we have. So true is better than false. Who cares? Actually, like you can basically have a negated goal. Don't destroy the world is an extremely good goal everybody should have. Right? Right? So really, the issue of delete effects in the original strips assumed that all preconditions are positive and all the goals are positive. It's not necessary. Okay. In fact, a more general idea would be to say that preconditions and effects are essentially state variable values. And if your state variable is false, you'll just say not of that state variable. State variable is true, you just write that state variable name. Okay. So in this representation, I'm actually using not in O1. And that's considered okay. Basically, assume that this is the normal, the generalized strips representation, slightly more generalized strips representation. In fact, with the conditional effects, it's actually, with this whole thing, it's actually called ADL representation. And ADL basically allows, it's a generalization of strips, it allows conditional effects, and it also allows positive and negative effects as well as positive and negative preconditions. Okay. But if I don't say anything, we can still think in terms of adds and deletes. Okay. Now I want to, given a description of a world like this, I want to be able to make plans. That's what you came for. You want to generate plans. How do you generate plans? That's basically most of today's discussion. Right? What happened? Okay. Now, if you ever want to generate anything, right, a formal way of thinking about it is, suppose you're trying to search for something. Search for something. A formal way of thinking about it, a zeroth order question is, if the thing that you're searching for came and bit you, would you recognize it? Do you understand what I just said? Oh, I'm searching for Rao. I'm searching for Rao. I have no idea who is Rao, but I'm searching for Rao. Now, if Rao comes and bites you, Rao should not be allowed to bite. But would you be able to recognize Rao? If not, what are you searching for? Do you understand what I'm saying? So if you're searching for anything at all, suppose you're saying, I want to write an algorithm for sorting numbers. You need to know what sorted sequence is. If I say, hey, here is a sequence that's sorted, you say, oh, Rao said it, maybe it's true. Then that's no good. Do you understand what I'm saying? You should be able to, at the minimum, in a formal sense, if I say this is the solution, if you think this is a solution, you should be able to verify that it is a solution. If you can't verify, then we are in philosophy, not in computer science. We are looking for meaning of life, but we have no idea. If the meaning of life comes and bites us hard, we have no idea what it looks like. But we just want meaning of life. Do you understand what I'm saying? So at the minimum, I want to know, if you're looking for plans, after all, what is a plan in this kind of a representation? A sequence of actions. Just a sequence of actions. So you're looking for a plan for this problem. The problem, by the way, in this case is, in the beginning, A and B are on Earth. Rocket is also on Earth. In the end, I want A and B to be on the moon, and A and B should be outside the rocket, so that they're sitting, that's why the moon is like that, so that the blocks can sit on them. Right? You always wanted that way, right? So the question then is, now you just need to make sequence of actions. And these are the actions. You can make an arbitrary sequence. And I'll say, here is a sequence. In fact, if you have an LLM, LLM will give you a sequence. There are two things you can do. One is LLM has been trained by Sam Altman. It must know what it's doing. So I'll just assume whatever it says is the plan. In which case you are in the wrong discipline, class, everything. You'll get lots of money, but you're still in the wrong discipline and wrong class. Okay. The other is, who the heck cares who came up with this? I want to check if it is a plan or not. I mean, you can do two things. One is, I'll just go ahead and execute this plan, and then you might die. In which case, people, dead men tell no tales. So nobody who is dead will get to yell at Sam Altman saying, your ChatGPT told me this is the way to do it, and I died. Of course, I mean, there is all these relations might try to sue him, hopefully one of these days, but not yet. Okay. So, but a cheaper way is you have a model. We are not even talking about real world. We are talking about, is the plan correct with respect to this model? So if I give you a strips model, and if I give you a sequence, can you check if it's a plan? Do you understand what I'm saying? And there normally are typically multiple ways of verification for anything. And here is a great way of thinking, actually, that if you know method M1 of verifying a solution, you can invert M1, make it M1 inverse. You'll get a search. You'll get a search algorithm. Do you understand what I'm saying? So in fact, this is a dumb way of always, any search can be thought of as, you should know how the candidate solutions look like. You generate them in some arbitrary order, okay? And then anytime you generate a thing, you check if it is actually a solution. You can play the same. I mean, you, the algorithm, can arbitrarily generate a sequence, check if it is true. If not generate on the sequence, check if it is true. This is generate test. It's the zeroth order way of doing sound planning. That means when you say it's true, then it actually should be a plan. If you don't care, if you just give a sequence and say, yeah, maybe it's a plan, check it out yourself, why do I need you? Well, I need you because you're ChatGPT and I've already paid $20 per month. So I might as well ask you. Do you understand what I'm saying? So you should be able to check. And whoever is giving the plan should be able to check whether the plan is actually correct or not. For every way of verifying a plan, if you invert it, you will get a search for plans. This has nothing to do with planning, honestly. For every way of checking that a sequence is sorted, if you invert it, you will get a sorting algorithm. Go back and try to think about, how many of you heard more than one sorting algorithm? Unless you have not taken any data structures. There are more than one sorting algorithm. Why are there more than one sorting algorithm? It turns out, actually, one easy way of figuring out is there is more than one way of proving that a sequence is sorted. Do you see what I'm saying? And for every possible way of proving that a sequence is sorted, you invert it, you'll get a sorting algorithm. This is a powerful metaphor. It will stand you in good stead in life if you realize that if I'm trying to search for something, first I need to know how to verify the thing. And for every way of verifying, if I really want to write a complete search algorithm, I just invert that verification, I'll get a search. Right? So if you think that way, here are at least 3 approaches for checking if a sequence that I give you is a correct plan for that problem, for that one-way rocket dump. Okay, first, let's just use your common sense. Suppose I basically, I assume that you know how to get this problem solved, right? First of all, right? I mean, give me a solution for this problem. me a solution for this problem. Yeah. People are so worried. What? No, there's no load A and B. You have to talk like the actions. Load A, then load B, then fly. That's it. The man knows how to go one way to the moon. Right? He may not come back, but he knows how to go one way to the moon. The rest of you are so worried about this whole issue of one-way rocket that you don't want to touch any action. What if you actually reach the moon and not come back? But really, that's a simple solution. If you don't even know how a solution look like, right? I mean, obviously, how did you figure this out? You sort of read this, you thought about English understanding or whatever understanding, and hey, that looks like a correct solution. But now you, for whatever reason you came up with this. This guy said load A, load B, and fly. Right? Right? At that point, actually, in fact, that's not enough. It's still not the case that it's still not completely correct according to his plan. I mean, let's give the correct plan. Load A, load B, fly. When you have flown, the blocks are still not on the moon. They're inside the rocket, which is on the moon. Unload A, unload B. Right? Right? So load A, load B, fly, unload A, unload B. Do you also realize that actually would load B, load A, fly, unload A, unload B? Will that work? Right? Because the way in which you load A and B, the order doesn't matter. Now, how about this? Load A, fly, load B, unload A, unload B. Would that work? No, because in fact, by that time the rocket has left. What are you going to load it into? So now we have seen some number of sequences, some of which are planned, some of which are not plans. You can kind of reason this out for this simple world. The question is, can you actually have a formal proof of verification? And if you have a verification proof, you can invert it, you'll get a planner. And the rest is all details. What is the details? A-star search details. Do you see what I'm saying? If I ever know how to verify, right, that's the goal test in A-star search. Right? If I know how to verify, then basically you can do generate test to begin with, or you can do better than generate test in terms of some child generator function, slowly make longer and longer sequences and see if any of those sequences wind up satisfying the goal test. Okay, right? So now keep that in mind. So I'll just take a small plan. This is obviously, you guys are smart. You know that load A, load B is not the complete plan for the original problem. Okay, but imagine that my new problem is a simpler problem, which is I want to have A and B inside the rocket. That's my new problem. The initial state is the same. I just want to have A and B inside the rocket. This is like a sub-problem. Right? Getting ready to fly. You just want to get both of everybody inside. Right? So simpler problem. So this is the one that we'll discuss. Okay, and you can discuss you can generalize this to the other one too. So one simple idea would be what's called progression proof. What is progression proof? You know the initial state. You apply the first action, load A. You get the next state. You apply the second action. You get the third state. And since your goal is in A and in B, you check if in A and in B are true in that final state. Just set check. Is in this final state in A true, in B true? If so, it's a plan. Then that's progression search. Okay. The other way is regression search, which is I will basically, in terms of, by the way, you can do this again for sorting too. For example, to say that a sequence is sorted, you will say every pair is correctly ordered. Versus I just only go in like forward to backward and keep checking that every immediately following number is bigger than the previous number. Or I can go backward to forward and say every immediately preceding number from the end of the sorted sequence is smaller or equal to the previous number. These are three different proofs. And they'll give you different problems, different sorted sequences. One of the weird things that you will realize is if you use the first definition, the sequence, if you just take a random number of numbers and you started sorting them, if you took the first definition, then the prefix becomes more sorted. And as the full sequence becomes the prefix, then you're sorted. Right? In the case of the other one, the suffix is always sorted, right? And if the suffix becomes the full sequence, it's sorted. The weirder thing is the pairwise comparison one. There, everything is kind of closer to its final position as you keep going from iteration to iteration. This is a harder thing to understand. Things like bubble sort work that way. You see what I'm saying? It's just a different way of thinking about what algorithms do. For every different way of proving that you have the solution, you have a different way of setting up the search. Okay. So anyway, for planning, this is the progression. This is regression. What is regression? Actually, and one thing I would say is, if this is the last action and in A and in B must be true after this, right? Essentially, I already know load B is the last action. I know that load B would give me in B because one of its effects is in B. So then in A must be in this, whatever, you need to make sure that whatever this state is in A must be true in that state. Furthermore, since you want to do load B here, its preconditions better be holding. What are the preconditions of load B? B should be on Earth, rocket should be on Earth. Actually, they should both be in the same place, but one way of they being in the same place is they both are on the Earth. You guys see this? That's regression. Okay, so this is like a state. So this is the approximate state I wanted. And basically notice that when I said this is a state, this is not really a state. You will never get a state where in A and in B are the only things that are true. It'll either be the case that rocket is on Earth or be the case that rocket is on Moon. That thing will have an actual value. That's why I wrote in A and in B in red and at RE in white. In general, the goals that we have in life provide a partial specification of the state you want to get into. Like many of you have a goal. I should have ASU degree. So you shall have ASU degree. And then on the day you have ASU degree, you find that you are like gazillion dollars in debt. You see what I'm saying? Right? You didn't like that. But that's okay. We still got you the degree. I mean, that was your goal. You have a plan, the plan reached the goal. So if you decided that gazillion dollars in debt is not a good thing to do, then you should have actually taken that. I should have the degree and I shouldn't have gazillion dollars of debt. At which point you just watch YouTube videos. Right? Okay. But these are side effects. In fact, most of people's worries about AI safety are that you provide the direct goals and the only real state worlds where those goals are satisfied, there are certain other bad things that you didn't like, but you didn't know that they would be. In every legal world where in A and in B is true, that thing will also be true. And you didn't like it. You didn't want it to happen. So if you didn't want it to happen, you should have said and not. So give me some examples of AI safety, crazy examples. What? What? Say it louder. I'm not able to catch you at all.
I have heard of a problem where AI starts to make paper clips and it consumes.
Yeah. Much better stuff is AI cooks cats. I don't even know why AI should cook cats. Cats don't taste well at all, I'm pretty sure. I'm a vegetarian, what do I know? But, so it's like, let's say, let's cook something, and AI cooks cats. Stuart Russell is extremely worried about this. In fact, Stuart Russell is the guy who wrote the Intro to AI textbook, and his current big thing in life is to make sure that AI doesn't cook cats. In general, AI, an agent, when given goals of achievement, will not also achieve certain other things that wind up being pretty badly negative to you. Do you understand what I'm saying? Now, you might ask, why didn't you say this? Well, you assume that people know that, like if you tell a person who is working at your home to make dinner for you, you don't expect that you have to tell the person, oh, by the way, don't cook the cat. In which case, that person will cook the dog. That anybody who needs to be told that they shouldn't cook the cat are probably very likely to cook the dog. Thankfully, you have people who know that when people want food to be made, they probably don't like pets to be cooked. You don't have to say it. Common sense. The common sense sub-goals, you don't have to specify. Do you see what I'm saying? And this is actually a big issue. So one of the big issues that becomes, that will be in the background is common sense sub-goal, common sense sub-goals. That means I'll tell you what my goals are, and then you will say these goals should be satisfied while a whole bunch of other side constraints hold. That they didn't need to tell you that those side constraints hold. Like, for example, I should get a degree, and you don't have to say I should get a degree and I should be alive. You see what I'm saying? Because that's considered, guaranteed, that's expected, sort of as a common sense goal. This is only true, by the way, for humans of our current society. Some other people may not care about going into debt while getting degrees. And some other people may not even care about being alive after getting the degree. I'm just talking about the normal run-of-the-mill humans who seem to have this hang-up about actually being alive after getting the degree, are actually having some bank balance after getting the degree. That's why it's your common sense. It's not Martian's common sense. Okay. In general, common sense goals, there are like two things that I'm saying parallelly. One is, normally whenever I say goals, there are other things I have in mind I didn't tell you. And in the case of the planners like this, there is no guarantee that those things won't go bad. And if you want to make sure that the other things that you didn't tell that you actually care about are captured, then you use this word called preference elicitation. Which is, yeah, I understand you want these goals, but what are your hidden preferences? Well, okay, hidden preferences, I don't want to die. I want to have a positive bank balance. How many times do I have to tell you this? It's like normal, reasonable preferences. In general, we will talk about how to capture those kinds of preferences in the classical ways, and that's a very painful thing. And the one good thing LLMs have, there are many, many things that are bad with respect to LLMs and planning. One good thing that LLMs have is that they kind of approximately capture common sense. Not guaranteed, but approximately capture common sense. Okay, that's like a whole entire thing. I'll just make a note here that common sense sub-goals, LLMs can help capture some. But having said that, I'll come back to this word where I'll say, you tell me exactly what you want me to achieve, right? And you better, and I essentially make sure that I will, that the algorithm, the verification checks whether in fact the solution achieves that. Right? Even for sorting, by the way, there can be side constraints. So for example, imagine I wanted to sort the students here in terms of their cumulative grade or something. It'll give large number of people might have the same cumulative grade. So every sorting algorithm is essentially going to just arbitrarily permute those people. But if I actually have a side constraint saying, I do want within the same cumulative grade, I want undergraduates first, and then MS students, then graduate students, then PhD students. That's a secondary constraint. That's a secondary tie breaking. And there can also be a tertiary tie breaking. Within the same undergrad students, people who have nice first names that start with SU should be higher up, let's say. That's my thing. So I have to say. This is what I mean. These are called side constraints. Normally for sorting, there is no obvious common sense sorting side constraints. But for living, for planning, there can be obvious side constraints that we all know, but the stupid computer doesn't. Right? By the way, the other thing that is like the thing that keeps people in AI awake in the AI safety community is Midas and his gold touch. King Midas, how many of you know the King Midas? Basically, for those of you from India, it's essentially Gandhari story from Mahabharata. Okay, equivalent. So King Midas basically keeps praying for the gods and that I want anything I touch to become gold. And because he thought that's like a pretty darn good way to do things. And essentially, then he has a pretty sad life. Because then, what a nice dog, dog becomes gold dog. And what a nice kid, kid becomes gold kid. And it turns out, while your parents think, I wish I had a golden kid, they don't really mean it. Seriously, right? If you actually become a golden statue, they would hate it. I mean, unless they really never wanted you to begin with. But so the point being that King Midas basically forgot to say things like two different ways, by the way. There are two different ways of dealing with these side effects. One is he forgot to say, and he assumed it should be obvious. Right? And the second is he didn't actually compute what are the other crazy things that can happen if he were to ask for this, and then give those crazy things as exceptions. That's inferential incapacity. Both are important. Okay. Having said that, now coming back to regression in A, in B, load B, I need in A should be present here because load B doesn't give in A. In B doesn't have to be present because load B is giving it. Right? And then its preconditions at BE, at RE should be present before. And then the thing that I actually come into this kind of discussion is that when I said in A, in B, and I put dotted boundary around it to point out that this is not a complete state. To point out that this is not a complete state. Here is a very interesting thing. Suppose there are n Boolean variables that are enough to describe your states. That is, that your states actually described on n variables. Right? If I say my goal is that variable V7 must be true. So if for n equal to, let's make n to be 10 for making things interesting. Okay. So n to be 10, you know that there are total number of states is 1024, or you're in the wrong department. Okay. So 1024. So now I say S7, I want it to be false. That's my goal. In the worst case, how many states are going to be consistent with S7 being false? What? Say it loud. 512. That tells you that when I give only a subset of state variables, like I did here, and I did the subset of state variables that I gave here, it's actually a state set. It's a set of states. Complete initial state is a single state. Goal state is always a set of states. Right? Now, here's a weirdo thing. If the initial state, you don't know what it really is, and it's a set of states, is your life going to be easier or harder? Generally, compared to normal planning. So you understood normal planning, which is you start from a complete initial state and you reach some state which satisfies goals, right? If you basically gave an initial state, I mean, that is actually partial. That means it only tells you of the 10 state variables, it only gives you values of 8 of the state variables. That means actually your initial state is one of 4 different initial states. That's bomb in the toilet problem. That's a planning problem where the planning problem is now harder. Right? But if I change the direction and I say the goals are partial, that means I don't care about, in fact, if you ask people, tell me exactly the complete state where you want your goals to be satisfied. Right? For example, suppose say that I want to get my MS degree, then I want the full state. What pants would you be wearing on that day? What shirt would you be wearing on that day? How much money would you want in the bank? How many cars? How many girlfriends? How many boyfriends? Everything. And you'll stop asking me to satisfy any goals after that, because it's just too hard to specify every possible thing. So in the case of goals, the fact that you can actually partially specify the goals is considered a good thing, not a bad thing. But it will actually come and bite you in the context of safety, because the stuff that you forgot to actually mention might have been important for you. You didn't realize. And then you might wind up getting into a goal-bearing state, which you didn't like. You know, the goal-bearing state of actually things do become golden when you touch them, but you didn't want your kid to become golden. You do actually have dinner, but you didn't want your cat to be the thing that made the dinner. I mean, that comprised the dinner, not made the dinner. Cat making dinner is completely fine. Right? Do you see what I'm saying? So in general, people think that having partial goal states is good, partial initial states is bad. And so this is actually a set of states. Right? I mean, notice the other thing, which is I could have just shown that this is progression, this is regression, and moved on. And it would have been much happier for you. But that's the difference between, first of all, graduate class, and secondly, my class. Because I will tell you all these other things that are actually important, and whether you use it or not is your life. Okay. So then at BE, at RE in A, so all this is saying is whatever is the final state, it better have these two. And then this is saying whatever is actual state here, it better have these. And then I actually regress overload A, and then it says whatever is the actual state here, it better have at AE, at RE, at BE. Because in A now disappears. And BE is added. I'm sorry, at AE is added. Honestly, this should have actually also had, the way I'm coming, if I was actually seriously coming back, this two is potentially a subset of goals. But then I check if all of these are already satisfied in the initial state. If it is satisfied in the initial state, I can stop right there. This is the grounding. If any time the regressed state is satisfied in the initial state, you're done. Similarly, at any time the final state that you have satisfies all the goals, you are done in the progression case. Do you see that? One is progression, one is regression, and you can do search with respect to this. Let's see. Before I go forward, Okay, I can come here in a minute, but let me show you. I'll skip over this right now, skip over this. Okay, let me show you with respect to this Bloxworld problem, unlike unlike the rocket problem, right? This is the one that we were looking at. It's the same thing. Right? So imagine I'm trying to actually have the following problem, which is A is on table, B is on table, A is clear, B is clear, hand is empty. And I just want B to be not clear and hand to be empty. B to be not clear and hand to be empty. It's a legitimate goal. You might say, what a weirdo goal, but it's a legitimate goal. I just don't want B to be clear. There, you might realize that there are many, many ways of not making, many ways of making B not clear. You put anything on top of B, B will become not clear. If you're holding B, B will become not clear. Right? I'm just telling you how Bloxworld works. That's like an extra thing that you get as a graduate class here. Okay, now the interesting question is, give it a minute and assume and ask if this is in this problem, can you make B not clear by putting something on it? Can you make B not clear by putting something on it? Right? You'll put A on top of it. Okay, at that time, is hand empty or hand is holding something? No, you can see all this. You can visualize all this stuff. Keep that in mind. Okay, simple. So I'm just going to do progression search. So this is the initial state. I wrote only the things that are true because by closed world definition, if everything has been, every state variable's value is known, I just have to write the ones that are true. Everything else is false. Okay, so then I can, in the progression, when you convert the verification into search, what you do is you slowly generate prefixes in the progression direction and check if any of the prefixes are already reaching the goal, in which case you're done. In the regression, you will generate suffixes and see if they reach the goal. In your doing generate test, you can just generate arbitrary sequences and check if they're actually happening to satisfy either either the progression or the regression proof. But if I'm searching for it, you do this finite differencing where, since anyway progression goes in the forward direction, might as well compute the prefix, and regression goes in the backward direction, might as well compute the suffix. Okay, so there I got pick up A, pick up B, and then if I do pick up A, I can compute the new state. Because I can check whether pickup A is possible or not by checking if its preconditions are holding. And if so, then I will write its effects on table, write effects which are on the red, holding A, not clear A, not on table A, and not hand empty. Those are all the things that happen if you pick A up. And the other things just come from behind, which is on table B and clear B. I put this thing, the red ones, with negative signs, but in fact, this is still a complete state. In progression, every state is a complete state because you start from a complete state, you get a complete state, which means I don't actually have to write the negated ones, but I'm just showing it to you. And then they'll come and then, you can ignore them. Okay. And then similarly, if I do pick up B, I get like this. And then essentially what progression is going to do is do a search like this. This is where the child generator function is pick a state in the frontier, expand it by actually adding, doing actions from the state and see if they reach. And then when you pick up that state, then you check if it is actually already a goal state. Okay, so that's progression search. The regression search, on the other hand, the regression search, on the other hand, so this is the progression planner. You have a child generator, which is essentially just adding actions. Okay, one advantage of this, there is, by the way, nothing wrong. You don't need this. There is actually a a sound and can even be complete. Generate test search, which is generate a candidate, check if it is a plan according to progression. Notice progression is just one way of verifying. You could do have, if you're generating, you could have checked whether it is progression or regression or any other thing, but that's one way. It's just that this is a lot more inefficient than this. It's actually systematically computing the prefixes. Right? Okay. Next is regression, kind of more fun. Remember what my goal is, which is not clear B and hand empty. Okay. And so I could, then the question, of course, is what are the actions I'm going to be regressing over? In essence, just as progression is saying, what is the next action that can be done? Regression is saying, what is the last action that could be present before this? What is the last action that could be present before this? Legally. Okay, so here, I can put down A. I can do stack AB, for example. If I do stack AB as the last action, yes, what do you need? Yeah, you have to wait until the break. Thank you. So you have stack AB as the last action, right? And then you would essentially be regressing stack AB over this state, and you know what the definition of stack XY is out there. So you would make sure that what does stack AB give among these two? Excuse me, you have to leave right now. It is a class going on right now. Please, you're distracting me. Thank you. So stack AB gives what? Not clear B. You agree? All of you agree? Stack AB gives not clear B. Right? Okay. So you don't need to write not clear B anymore before stack AB. But you still need to write hand empty. So stack AB, sorry, okay. Stack AB, before stack AB, yeah, hand empty. I wanted hand empty here, right? 1 second. This is actually a problem. Is this the correct state? Stack AB, not clear B, and holding A before. Okay, after that. Well, actually, after stack AB, hand empty is also true, interestingly enough. Stack AB gives both of these. Do you guys realize this? When you put A on top of B, now you're no longer holding anything, so your hand is empty, and B is unclear. So it gets both words with one action. But you're not done. You have to make sure that its preconditions are holding, and its preconditions, stack AB's preconditions are holding A and clear B. You need to search back from that. Similarly, you can put down A. If you put down A, then what happens? You will be having hand empty, because if you put anything down, your hand will be empty. I'm just thinking like computer, right? Your hand will be empty, right? So hand empty doesn't have to be taken back, but not clear B has to be taken back. And then to put down A, you should have holding A to be true before. So this partial state is not clear B and holding A. How many of you see that this is a dead state? There is no legal blocks world state that will have B not clear with only two blocks, A and B, that will have B not clear and A is being held. Who is sitting on B? You see what I'm saying? However, most of you, if I didn't point out, you'd have thought, oh, yeah, that's a reasonable thing. I'll just continue expanding that too. If you know anything about search, the worst thing a search algorithm can do is to expand a dead node. Dead node will have dead children nodes, will have dead grandchildren nodes, dead, blah, blah. It's like a whole entire dead descendant tree. And you are making huge progress, but you're gone. You're not going to be able to find any solution under that subtree. My point is, under this, if you actually just turn this upside down, that looks like a search tree. This is a top initial state, and there's like a substate. And below this substate, there can be a huge subtree. That huge subtree is dead. You see what I'm saying? In the sense, none of those states are actually ever reachable in the blocks world from any legal initial state. In this particular legal initial state. If you realize it, you could kill it and your search can be improved. You understand what I'm saying? But how will you realize this? That this is actually dead? What? Okay, so what would the validity function look like? In general, if you want to say, so basically think of what you're just saying, okay? This is a goal state. It's a sub-goal state. It's a partial sub-goal state. If you know that sub-goal state can never be reached, you can kill it. How do you know that it cannot be reached? I'll give you an example, okay? One idea is I can have a goal state which says A and not A. It cannot be reached because you can't have two values for the same state variable. Simple. But I want a general solution. I want to be able to see if a particular substate is actually not reachable, in which case I can kill it. How hard is it? She is saying there is some magical validity function. And the question then is like that black box. Remember the black box in the planes that is indestructible? Why don't they make the entire plane with the black box? Right? Whatever is, who is the one who's saying the validity function? Yeah. Why don't you use that validity function to do the search to begin with? My point is planning is reaching a goal state. This is just the what's called the conjugate problem, saying the goal state cannot be reached. You see what I'm saying? So actually the way to prove think about this, the way to actually say that a general state cannot be reached is to actually sub-goal, and that being the goal state, use a complete planner, let it keep going, and then it says, okay, there is no actual sequence that can reach this goal state. At which point you'll come back and start doing the normal planning. But you already did a lot more than normal planning. How many of you understood what I just said? This is extremely important trade-off in search. Right? In general, you could either be checking that the goal can be reached, or you can be checking that a particular sub-goal state cannot be reached. And if the sub-goal state not being reachable, if you needed completeness, it's actually extremely hard. It's just as hard as planning. In fact, conjugate problems are generally harder. By the way, coming back to LLMs, because we can't not talk about LLMs every once in a while, the best way to kill them is to give them a problem that has no solution. because they have been RLHF to death. They will never tell you there is no solution for what you ask. They'll give you a made-up solution. So in fact, if you give unsolvable problems, in fact, this is an unsolvable problem. If I have an initial state and this is my goal state, that would be an unsolvable problem. It's an extremely simple 2 blocks unsolvable problem. And it took me this long for me to make sure that you recognize that it is actually unsolvable. Because to actually see it's unsolvable, you have to try all possible ways of reaching that goal and find that you actually cannot. And more importantly, the search process you are using to do that has to be exhaustive. This is very important. To say that a plan exists, if you're just lucky and you're just guessing a plan and checking, you're guessing a plan and checking if it's correct. You know, the whole lottery thing essentially is you buy a lottery ticket, you win, well, it's won. To say that something is not reachable, you need to actually, so for example, you want to show that Arizona has a state lottery which is actually unwinnable. What are you going to do? All of us will buy tickets and none of us win. Can you prove that Arizona state lottery is unwinnable? No. It only just proves that we are stupid to begin with, because you should never buy lottery tickets. Lottery tickets are a tax on stupidity. Right? Right. Okay. But the point is, how do you prove that the lottery is unwinnable? You actually have to do if there is no ticket that can actually be sold that will ever win this lottery. For example, all the tickets have 18 digits, let's say, and they're only going to pick 17 times the pinball. Or all tickets have digits between 0 and 9, and their pinball only has 0 to 8. You see what I'm saying? Or some things are missing, for example. Actually, that doesn't prove that it's unwinnable. I mean, there are other ways of proving unwinnability. But in general, my point is conjugate problems are in some sense harder than just finding the goal, because you can be lucky and found a solution to the plan. To show that it cannot be solved, you need to check all possible ways of achieving that goal and say that none of them work. That's much harder. Okay. So that's regression search. So it turns out that actually, I mean, the stuff in the back tells you how to, just as for the progression you said, put the action whose preconditions are holding in the previous state, and then compute the next state by essentially writing down the effects of the action plus copying over everything else. That's what we said. For regression, this is what you say. You can actually regress a state S over an action. Okay, so here is an interesting thing. What happened to this branch? I wrote this branch, put down B. None of you asked, why didn't I expand this branch? Huh? What happened? No, put down B, what happens? No, I can do put down B in that. No, I'm not talking about going forward. I'm going, if put down B is the last action, why can't it be the last action? Because if that's the end of the world, then B is actually going to be clear when you put it down. Okay, this is making up stuff. This is LLM world. Where, yes, you gave me a specification, but I will start hallucinating all sorts of other things. Unless my rich uncle gives me extra blocks. Right? Unless I get to define clearness in my own subjective way. That's not allowed. I mean it in a serious way. Okay? There is no unless, because that's the point about formal specification. This is what the world is. If you wanted another world, this is not the model for that. Do you see what I'm saying? So why did I not do put down B? Because if I were to do put down B, it doesn't give either not clear B or hand empty. No, it gives you hand empty. Put down B will give you hand empty. So it requires still not clear B. And then its own preconditions, which is so it gives no, put down B gives, yeah, so not, it doesn't give not clear B. So actually, so sorry. The reason I would not do this is if I were to do put down B, it will actually give clear B. This is the very last state, and if it B is clear now, it can never become non-clear. So that's what the thing is saying. There is no variable V such that V is given different values by the effects of A and state S. Here is a variable clear B, it's being given an effect positive and a positive value here, and the state gives a negative value. That's impossible. Especially because it's a very last state. There's no way of getting out of it. So in such case, if such a variable exists, you won't do the action at all. Just as in the progression, you would not have done the actions whose preconditions are not holding in the state. Right? Okay. And then the next thing is there is at least one variable V dash such that V dash is given the same value by this action as well as the state. The first one is do no harm. The second one is do something useful. Do you understand what I'm saying? So, and in fact, there is a reason why. So this is do no harm. And this is do something useful. Right? Do something useful. Okay. So if both are holding, then you will put the action in. If those two, if I must give up on one of the conditions, which would you rather give up? If you must pick, doctors should do no harm and also make you better. It turns out that the world only contains either doctors which will do some harm or doctors who don't actually do anything useful. You only have those two doctors right now, and you have to pick one. Who would you pick? At least they should kill you, right? Hoping for the other doctor to come to town. Right? So you should never, if you must give up, you should give up on the first condition, never the second. I'm sorry, must give up, you should give up on the second condition, not the first condition. If you ignore the second condition, all that will happen is there would be actions in the plan. They are just irrelevant. They're not needed for the goal. They just become non-minimal plans. Imagine everything else remains the same, but there is an action called paint block. And the paint block changes the color of the block to black. That's it. That's all it does. I can do paint block as an action. It's just not doing anything useful. It's not killing the plan, because after the paint block, you will still try to solve the planning problem. Whereas if you put this guy as the last action, you're dead. There's nothing you can do before this that will make sure that after this, you will still reach the goal. Do people understand that? Non-minimality is better than the plan will never actually be, there will not be a plan. And this second one, if you ignore the second one, you get non-minimal plans. That is like optimality conditions. We haven't talked about it. We're just talking about, reaching the goal, but we can also talk about reaching the goal with the fewest actions. And actions that are not doing anything useful are basically going to increase the length without actually giving you any useful effect. Yes.
One of the block is
have a lot of dead spaces where the planner might paint another block black. Let's say we wanted to.
It's not dead. It is doing useless stuff. Oh, yeah, come on. All of search is trying to do more optimal search. I understand that. Okay. All I'm saying is by doing painting of a block, you will get a state from which there is still a way to reach the plan. No, but remember one of the things. I just added this completely extraneous action called painting. I have a color. I'll just put a color variable. But color is not actually important at all with respect to you can see, I mean, in this given case that being things on top of each other, being clear, have nothing to do with color. It's an irrelevant variable. If you increase the number of variables, you will blow up the state. And you can spend a lot of time doing stuff with those variables. It looks like busy work. And the boss thinks, okay, the kid is working very hard. Right? Do you see what I'm saying? And thankfully, at least after you're done, they'll get somebody else who can actually solve the problem because you didn't screw up the whole thing. The worst case is instead of doing busy work that is not, that leads to non-optimal thing. That means basically you're not completing the program. You actually write a bad program and put it on the flight. And then your boss and their company will go down with it. Do you understand what I'm saying? So do no harm is very important. When you take your software engineer jobs, please do no harm. Right? If you do good, but at least don't do harm. Right? I mean, if you are not sure what you're doing, just at least kind of look very busy. Like this, and then they will think you're doing something, but don't actually submit the code, or at least submit the code with improved comments, like improve the number of comments in the code. That's always a good thing to do. Right? Because when humans can read it, obviously computers will be much better. Right? But this is the point. These are actually irrelevant actions. And in normal world, there can be irrelevant actions. And this simple thing might allow you to do the irrelevant actions. It doesn't stop you. Well, actually, the second one will stop you because it says it's not useful. Okay. And then the resulting state as dash is computed by essentially making sure that every variable here, which has the value that is consistent with what this guy is saying, it doesn't need to be copied back. Every other variable will have to be copied back, but you already made sure that its value is not something against what that last action is saying. Plus, you finally also write all the variables that are listed in the preconditions. This is regression. Regression is already kind of a strange thing. You see what I'm saying? Regression already is a strange thing. On one hand, actually, let me say this. I'll come back to this, come back to this, come back to this. Yeah. Let's do this discussion. Progression is this way, regression is this way. Which one do you think will win the race for efficient search? Right? You know A-star search. Give me some arguments as to why which of them will win. It's useful for you to have intuitions about what search algorithms are likely to be efficient. As they can just randomly doing some amount of search and then writing some amount of tables and hoping for the best that the paper gets in. Do you see what I'm saying? Okay, give me some examples. I would say, I'll start. Regression has a lower branching factor. In a realistic world, many more things can be done from the initial state than are things that are actually relevant in any sense to the goal state. I mean, you never wake up in the morning and say, let me see what all the things I can do. You can do this, you can do that, you can actually put on your socks, you can pour water on your head, all sorts of things you can do. Infinite number of things that are actually feasible. But like the most important thing is to plan to be here at 1:30. And everything else is wasted effort. So you should start thinking, what should I be doing now such that at 1:30 I will be in the class? That's actually between the progression and regression. Regression is the only thing that actually looks at the goal state in trying to decide the search. Agreed? So regression must win. Compared to progression, progression has a much higher branching factor, regression has a lower branching factor, and everybody from the little kid onwards knows that search is B power D, bigger branching factor. And D may be the same, right? D is the depth, and you can imagine that you can assume that is bounded by the actual solution length, in which case D is approximately the same for both, which is actually not true. So if it's a bigger B, then you have a higher search cost. But then I'll say progression searches in the space of complete and consistent states. You just found this. Regression, on the other hand, searches in the space of partial states. How can you say partial state is a bad thing? Here is an interesting question. If there are n state variables, how many complete states are there? If there are n state variables, how many complete states are there? 2 power n. The complete states, that means by definition, if I give a value for each of the state variables, that is a complete state. I don't know what you mean by complete. This is my definition of complete. No. Complete means it's just a state. It's completely specified state. You know which state you are in. Okay, 2 power n. If I am looking at this kind of states, which is partial states, how many states are there? Who said? 2 power n plus 1 is this, I don't know, which one is this? Is this, I'm sorry. Is this 2 power n plus 1 or is it 2 power n plus 1? 2 power n plus 1. So that means double the 2 power n plus 1 is nothing but 2 times 2 power n. It just doubles. This guy says it doubles. Who is with him? By the way, this is graduate class. I'm talking elementary math, seriously. This is combinatorics. So what are we really trying to figure out? First of all, can somebody tell me why are there 2 power n states when there are n state variables? Yeah, because the first state variable can be true or false. 2. Second will be 2 times 2. Third will be true 2 times 2 times 2, etc. 2 times 2 times 2 times 2, n times 2 power n. Do the same argument now. For any given state variable, you will know that it's false. You'll know it is true, and you don't care. There are 3 possibilities now. 3 times 3 times 3 times 3 times 3, 3 power n. There you go. Regression searches in the space of 3 power n states. Okay, and so it's not clear that regression will actually win. In fact, if you don't use any heuristics, oftentimes, generally, regression fails compared to progression. Even if you use heuristics, actually, it's not as obvious, but we'll get to that. Okay, there are 3 power n partial states as against 2 power n complete states. Weird scenario. You see what I'm saying? By the way, would you say 3 power n is really sad, or it could be much worse? Is 3 power n very sad, or it could be much worse? I mean, one way of making your life easier is, oh, I could have been, but for the grace of God, I could have been much worse off. Right? Right? So there are 2 power n states. If I say a partial state is just a subset of states, then how many subsets of 2 power n states are there? how many subsets of 2 power n states are there? 2 power n. That should be enough to wake you up and not go back to sleep. What gives? How come we did not deal with 2 power n? We're only doing it at 3 power n. Because it actually turns out that actually the most general case is 2 power n. That's the number of belief states. If you are looking for syntactic states, which all states are determined only in terms of not clear, basically there is no disjunction involved, and it's just basically saying it's not clear B, hand empty, and so, a state variable is either given a value, not given a value, given a true or given a false, or not given any value at all. If on the other hand, I actually go pick an arbitrary subset of 2 power n states and say any of this subset are the goal states, everything else is not goal state, then I have 2 power n ways of doing that. There is no bearing anymore. Looks like things should be easy, but they're not. Things should be hard, but they're not. That's what you understand. Essentially, when you understand the computational complexity points of view, then you will understand these kinds of things. So the last thing before we'll take a 15-minute break, I just want you to think about this. So I want to show you this, and then I'll set you off for a 15-minute break. So remember, we had two proofs. We inverted each of the proofs, we got searches. You completely understand now, right? I just basically inverted. Everything else is a detail, really. In fact, the way that whole regression, when do I put a action back, etc., that's actually unnecessary. If you just wanted a sound planner, you could just randomly guess an action sequence, check if it actually satisfies the regression criterion. If so, you're done. It doesn't really matter. But you're just trying to generate the search tree such that you can avoid generating things that are already dead. Right? Because any action sequence, imagine the initial state is such that A1 can never be the first action because A1's precondition is not holding in the initial state. So any action sequence that starts with A1 is going to be dead. Generate test will essentially generate a whole bunch of A1 based action sequences and then keep on saying, yeah, they're different. This one is A1, A2, dead. A1, A3, dead. A1, A3, A4, dead. The real reason it's dead is because A1 can never be the first action. Whereas if you compute the prefix, you will realize this. That's what the search is doing. So there is a difference between soundness and efficiency. So the last thing that I want to do before the break is there is a completely different way of thinking about correctness of plans, which I bet is what you do. I bet that you do not check whether your plans are correct or not. By either of these methods. If you're thinking of real life plans, you certainly don't do regression. That just hurts your head. Right? You probably are not doing progression either. How are you coming up with plans? I mean, introspection is the lousiest form of psychology. Let's get it out there first. But having said that, I would say you probably think more like this at any rate, which is, here is the initial state at AE, at BE, at RE. Here is the goal state, or these are the conditions that should be finally true in A and in B. I think in terms of causation. Somebody must be making in A true. Right? So if there are actions here, one of those actions must be making in A true. I would actually argue that it turns out that the initial state itself is an action called A0, which has no preconditions, and it has these as the effects. It's like a made-up action. Okay. And then similarly, the final state actually has an effect called done, and its preconditions are the goal states, the goals. Actually, in general, so if you think of this as A0, you can think of this as A infinity. These are dummy actions. So every plan starts with A0, ends with A infinity. There are more actions in the middle. Those actions can no longer be A0 and A infinity because those can only be in the beginning and end. They have to be one of the normal actions from the domain. And if I gave you these as the actions, I should make sure that every precondition of every action is supported by some action. Support always goes in the causality goes forward in time. It doesn't go backward in time. That means whoever is trying to support in A better be coming before A infinity. Whoever is trying to give me in B better be coming before A infinity. And now for these actions, they also have preconditions. I didn't write it before, but load B has at BE at RE as preconditions. Load A as at AE at RE as preconditions. You need to support those too. One good thing is the supporter can also be A0. A0 is a dummy action that is basically the initial state is supporting the condition. This is basically what we want, right? I mean, if you're trying to make a party and you say, I need drinks, I need chips, I need whatever the heck, let's say, okay, Tom, you get the drinks, John, you get the chips, and Mary, you get whatever the heck. And then you have three people. Three things, three people. You could also say, Tom, get all of them, in which case Tom will not come to the party next time around. But it is possible. That's how you make parties. The interesting question is, that's first of all the causal link. This is basically called causal link. So load B has an effect in B that is supporting here in B at A infinity. So I will write this essentially in this following form. Load B gives in B to A infinity. That's a causal link. So every precondition of every action must have a causal link supporting it. Part one. Part two, right, is after the action starts, one action says, I will support this condition. No action that can possibly come in between should delete that condition. Do you understand what I'm saying? No action that possibly comes in between should delete that condition. Then the condition has been established and it has been protected. This is what is needed to achieve goals. Do you see what I'm saying? So for every condition, there should be a causal link, and every causal link, for any causal link, if a causal link is of the form A, P, B. I'm sorry, A1, P, A2, let's say. A1 action gives condition P to action A2. Then every action that can come between A1 and A2 should not delete P, or should not have an effect that goes against P. This is basically what you do. You will say, I will get this condition with this, I'll get this condition with this. I'll make sure that nothing comes in between to kill this particular causal link establishment. Honestly, I would say this is as good as like the bubble sort kind of a thing for sorting. You're no longer thinking about prefixes and suffixes. You're not talking about prefixes and suffixes. You can put any action anywhere. The precedences between actions come only because of causal links or because without that ordering, some guy comes in between and will unnecessarily violate some condition that's being. So don't get out of the way. You keep telling your friends, get out of the way. They are threats. You're trying to achieve something, and they are basically, instead of actually helping or not doing anything, they're getting in the way. They're actually violating the condition that you're trying to establish. You say, get out of the way. You get people out of the way. So if A1 gives P to A2, right? Let me write this. If A1 gives P to A2, and there's an A3 that has basically, let's just say, says if R is true, then I will give you not P. Remember, we talked about conditional effects, which you have forgotten for a while. I'll bring it up. If R is true, then I'll give you not P. This is your friend who is getting in the way, A3. You need to get them out of the way. How do you get them out of the way? One is you make A3 come before A1. It's called promotion. They should necessarily come before A1. The other is you can make A3 come necessarily after A3. Only one of them, either this or this. That's called demotion. You're demoting in the ordering. And then there's this other thing. If I don't do those things, there is another way of making sure that A3 stays but won't get in the way. Can anybody realize that? It's only going to say not P if R is true. So what can you do to stop them? What? No, A is already in. I mean, I understand sometimes we hope that our friends who are annoying disappear, but that has court-related issues. You don't get to disappear people. Do you understand what I'm saying? This guy is there. A3 is going to be there, and who is threatening, if you give me R, I will make sure that P is false. So what do? Why? That's actually, that, by the way, is a strange enough thing. That guy said, interesting thing. He said, if A3 is anyways going to kill, then I will put an A4, which will give P back. We will get to this. This is, by the way, it's called white knight. It's a beautiful idea, weirdo idea. Because if A4 is giving P and A1 is giving P, who is actually giving P? And you're also in this form where you can be dead for a while and you can come back to life. You're saying, you see what I'm saying? P would become false for a while, and then I'll quickly, A4 will come and make it true again. It is actually doable. It turns out it's called white knight condition. You bring it back later. But there's a much simpler idea. I don't know why you can't think about it. If I say that if you keep paying attention to me, I'll go on and on and on. And you want me to stop, what would you do? What? Don't pay attention. If you give P, I'm sorry, all I'm saying is if you give me R, I'll give you not P. So I will make not R a precondition of A3. It wasn't an original precondition. You see what I'm saying? Not R becomes an extra precondition of A3. This is just to make sure that you won't do the bad things. Like, for example, the friend is there, you will tie their hands so that they won't get into trouble. What? No, but A3 must have been there for some other reason. All I'm saying is A3, it's currently in the plan, unordered with respect to A1 and A2, and it is getting in the way of this causal commitment you have between A1 and A2. To stop it from creating mischief, you're basically, kind of tying its hands. The way you tie its hands is actually saying not R. So I said the first one is promotion. This is demotion. And this one is called confrontation. The most beautiful terms. You confront the evil and say, I will remove your ability to be evil. Right? In the sense, I'm going to shoot. I'll remove the bullet from your gun beforehand. We could have saved lives in Georgia. Do you understand what I'm saying? I mean, you can't disappear a kid, but you can remove guns from the damn home, or at least remove the bullets from the damn gun. That's confrontation. One last thing. This looks as if the discussion looks as if I only use conditional effects for confrontation. But suppose I actually need to support A2 requires P, but A4 says if Q, then P. It's not giving P directly. If Q, then P. Then I will just make Q a precondition. Do you see what I'm saying? And then somebody will make sure that Q will be true. In fact, in the one-way rocket domain, this is what is going to happen. The fly will say that you will be on the moon if you are inside the rocket. And so I'll make inside the rocket as a precondition, causative precondition. And then somebody will make sure that that will be satisfied. Let's take 15-minute break. Come back, maybe 15-minute break and come back and we'll talk about this particular. Okay, I think we will get started. I think I'm supposed to start at 40, so I'll start. I think there are probably some people are still coming in. So this is just a repetition of what I was telling you earlier about supporting. Pay attention, guys. So you're basically supporting P to A2 using A1, which has a conditional effect, Q, if Q, then P. And so to do that, I will make A1 come before A2, right? And then I'll put its causal link saying A1 is giving P to A2. That's my causal commitment. And to actually make sure that it gives P, it won't just randomly give P. It'll only give P if Q is true. So I will make Q a precondition. This is a secondary precondition. In addition to the executability preconditions, there is this additional precondition. Just like the executability precondition for a flight is that there is a pilot, there is fuel. You being in the plane is a secondary precondition. It's only important because you want to be in Detroit. They would go to Detroit whether you are there or not. If you want to make sure that you're going to be in Detroit, you will just basically make sure that you put yourself in the plane. That's a secondary precondition. This one is called causative precondition. It makes the action actually cause. Do you see what I'm saying? Okay. And so if you don't have any precondition, that basically means you're always going to give that. If it's a non-conditional effect, you'll unconditionally give P. If it's a conditional effect, you have to cause that P. One of the weird things, actually, when you're talking about conditional effects, honestly, is while you can only give unconditional effect once, you can give conditional effect in many different ways. For example, I can have an action A1, which says Q implies P. Keep. Which says Q implies P, and it also has another effect, R implies P, another effect, W implies P. These are all the different ways in which P can be true. So it turns out each of those is a different way of making P true. I was telling somebody an example that if you want to be in Detroit when the plane takes off, you can be in the passenger seat, you can be in the stowage. You do know that people actually kind of get from place to place when there are immigration problems by actually going into the stowage, and then they do actually go with the plane. You can hang on to your dear life to the wings. And that's a somewhat robust, non-robust effect, but stowage also is a non-robust effect, but at least you will reach, your body reaches Detroit. You may or may not be alive. With the wings, unfortunately, your body also may not reach. But notice these are all conditional effects, different things. And so if you cannot actually afford a passenger ticket, or you don't have a passport that unfortunately allows you to get the passenger ticket, you might very well consider the stowaway thing. That's a conditional effect too. So then there are three different, same action is basically giving P in three different ways here. Right? So in the case of causation, I only have to select one of them. So either I have to select Q or R or W. Any one of them will give P and make them as a precondition. And more generally, I could have actually written it as Q R R R W. That would be what's called a disjunctive precondition. But then making disjunctive precondition true, you will split it into the search space anyway. The other option, on the other side, A3 is basically threatening to blow up P. It says R, if R is true, P will be false. I can deal with that threat either by putting P before A1, A3 before A1, or A3 after A2. Okay. By the way, these are called precedence relations. And it's written this way, A1 precedes A2. As against A1 is immediately before A2. They're like cemented on together is contiguity relations. In progression and regression, you make contiguity relations. You're making a prefix one side, suffix in the other side. Precedence, on the other hand, is essentially saying A should come sometime before B. Other things can come in between. This is reasonable, right? You should put on your shoes. You should put on your socks before your shoes. Nobody said that as soon as you put on your socks, you should put on your shoes. You can put on socks, hang around, some dance, and then, eat breakfast, then put on the shoes, completely fine. The world is not going to end. Yes. What do you have? Circularity, you mean? What did you say? Uh-huh. No. So actually, there are three very different ways of making sure that A3 won't be a threat. One is don't do anything to the conditions at all. Just put A3 to come after A2. That means you put a precedence relation between A2 comes before A3. Alternately, you can do A3 comes before A1. A third alternative is put not R as a precondition for A3. Not R as a precondition for A3. Okay, now the interesting thing here is just like that guy has W gives P, R gives P, Q gives P, this guy is also a multi-headed threat. Okay, R gives not P. By the way, yeah, this R, that chart should not have been the same. Maybe I should have called this R dash, just call this R dash and then This will be R dash. Okay. So this R implies not P, J implies not P, K implies not P. Right? Now, in this case, you don't get to choose just one. You see what I'm saying? Because if either K, R, J, or R are true, P will be violated. And since you don't know what will be true, if you're not planning for it, anything can happen before this action. So in that case, the preservation precondition will be K and J and R. You see what I'm saying? Either you get A3 out of the way, demote or promote, or if you keep it in the middle, then you stop all possible ways in which it can disrupt you. Right? It's not just one way. If it is causing, just one way of causing is enough. If you're stopping disruption, all disruptions have to be stopped. And this is called preservation preconditions. And both causative and preservative preconditions are secondary preconditions. That means they're not executability preconditions. In fact, one can argue that there is no such thing as actions not being executable. Actions are always executable. They just may not have the effects you want. Suppose, for example, I'm going to lift this, this little thing with my index finger, right? I'm lifting it right now. You can't see it, but I'm lifting it. The world didn't end, right? It's just that the world didn't change either. Actually, it changed a little bit. I mean, I'm kind of putting pressure on my index finger, but the world that you can sense hasn't changed. The table hasn't changed. So in fact, executability preconditions are a special case. In some cases, you can always try to, start the car, even if you don't have engine. It just won't go anywhere. It's not like if you're trying to start the car, the world will say, don't even try because you have no engine. No such thing. Actually, interestingly enough, executability preconditions make search easier. It's like a third order effect, because it turns out then you can just say that if you can't even execute, then you won't use that action. Imagine the whole thing about progression was you'll only pick those actions that are executable in the initial state, right? If you don't have any executability preconditions, every action is executable in the initial state. It just won't have any useful effects that you think normally are supposed to happen when you do that action. In fact, you can argue that a different way of writing strips actions is either you can say normal strips action can be written as PR gives QJ. Let's say that's the normal precondition, executable precondition thing. I can just change it as A, P and R implies Q and J. All of a sudden, the second action is always executable. It will only give you Q and J if, in fact, P and R are true beforehand. If not, it won't do anything. Do you see what I'm saying? Real world actions are more like this. It's not like there is any action. I mean, the whole thing about executability preconditions is an abstraction that we make up. But really, you can always do the action. It just won't have any effect. Okay. And then the last thing that I was going to say, so that was about the causative preservative preconditions. The other things that somebody was asking, and so I wanted to go into this. This is from the beginning of the class, and actually it blends well into this. A way in which, given all this discussion, we can say when actions written in strips representation will be less, won't be compact compared to the atomic actions. That's what we were discussing before, right? And I would say there are two conditions you can at least be aware of. One is an action affects only a few variables and in only few different ways. Like, for example, this guy is affecting P, but in 3 different ways. Do you understand what I'm saying? If it is affecting few variables in few different ways, then the strips representation will be way more compact than the atomic representation. And the other crazier thing that, again, some kid asked just now, I'm sorry, even though you're grad students, I'll call you kids because I'm 62, so everybody is a kid for me, is it actually the case? Is it actually the case that the upper bound of the action size will always be the atomic action? It's a good question to ask. Mostly true. But since anyway you're sunk, I'm going to tell you a third order interesting point, which is that a given action, given atomic states, every action has a unique representation. It's just a matrix. It's a matrix of ones and zeros. There's no difference. I mean, beyond the fact if you put S1, S2, S3, and S1 to Sn here, S1 to Sn here, that's just a unique representation of the action. On the other hand, the compact actions could actually start getting written as an arbitrary logical formula gives rise to a non-disjunctive logical formula as a conditional effect. Notice that disjunctive preconditions are allowed. It's only disjunctive effects that are not allowed if you want to be deterministic. Disjunctive preconditions can be pushed into the search tree. So if I give you 2 actions, they both can potentially correspond to the exact same atomic representation, but yet they look syntactically different. And this should not be surprising for those of you who kind of have some idea of propositional logic. Let me see if I can get a free page. Yeah. I want to make this connection to propositional logic here, that imagine there are n propositions and Boolean propositions. There are 2 power n worlds, that is interpretations. A propositional logic formula, however arbitrarily complex it is, it can be A implies B, R bracket begin, C implies D, R bracket begin, J, R, Q implies M, etc. All that stuff is just some random Boolean logic formula, right? Every propositional logic formula has a unique set of worlds where it is true. Every propositional logic formula has a unique, this is for propositional logic. There are only 2 power n worlds. Any arbitrary propositional logic formula that you write will be corresponding to a subset of these worlds, including the empty set. Including the empty set. There are only, so basically there are, that basically means there are 2 power n subsets, 2 power n subsets of worlds, right? And every propositional logic formula corresponds to one of these subsets. But the reverse is not true. Given 2 propositional logic formulas, they could be equivalent. They don't look equivalent, They don't look syntactically equivalent at all, but they're actually the same. In fact, here are two propositional logical formulas which are syntactically different, but semantically the same. Right? If you could see this coming and you just remember it as a mugged up fact, then imagine an arbitrarily large propositional formula, another arbitrarily large propositional formula, you're trying to check whether they're equal or not. They're not, I mean, it's not easy. It's not. First of all, there are multiple ways you can write syntactically different but semantically equivalent logical formulas. That same thing comes with the action representation, essentially. You can write multiple syntactically different, semantically the same in the sense of atomic actions underneath. Compact formula, compact action representations. Now, what does it mean to say semantically unique actions? Why would that, how do you make that happen? How do you make that happen? You can't make that happen in propositional logic. Like you can't, if you have propositional logic, these are two syntactically different formulas, right? They're same, right? How are you going to stop this from happening? You're going to say, so you have to make some random requirement. It's possible that you make some syntactic requirements such as actually one thing you could do, which is basically, you may or may not be thinking about it, but I'll give you the benefit of doubt and say there are normal forms. Or canonical forms. You can take any arbitrary propositional logical formula and write it in a CNF version or a DNF version. How many of you actually done the intro to AI class? How many of you know theorem proving? To do theorem proving, you convert the propositional logic statements into CNF formulas. CNF formulas are a conjunction of clauses where each clause is a disjunction of literals. And then you start doing, resolutions on that. That sort of a thing can reduce some of the syntactic ambiguity. Okay. There you go. Okay. So basically this is the other piece that I just wanted to add about when the actions can be larger in the compact 1, 2. And then the last thing that I'm going to do is essentially, now you know how to prove a plan to be correct using causal reasoning. I mean, this is like one of the other things that people think they should know LLMs, how to say LLMs, how to say prompting, how to say layers. And then also a little extra is how to say causal. We are into causal reasoning. Okay. Unfortunately, causal reasoning is a bigger deal for learning from data because mostly you learn correlational information and it's not obvious what causes what. But in our world, we actually have causation staring at us. Do you see what I'm saying? If I give you the model, right, the action has preconditions and then effects. Action causes the effects. And that's why the link is called causal link. A is actually causing B. A is causing P to be true until B. So causal link proof is this for all proof. For all preconditions of all the actions in the sequence that you have been given, prove that each of those conditions have a causal link, and the causal link is actually not violated. If you can prove that, then the plan is correct. This actually gives a very different way of proving the correctness of a plan. Way different way of proving a correctness of a plan. And it's actually very useful. If you already have a plan, something goes wrong and you want to replan, it's way better to think of what went wrong and actually just fix that. And if you're fixing by putting extra actions in the middle, it's not progression, it's not regression. It's something in the middle, right? This is how we actually do replanning. So replanning, basically thinking in terms of progression and regression, is just a dumb way of doing it that way. So it's a much simpler, much better way to do it this way. And I will tell you how to do the search here. It's a much more little more complex looking thing. And I'll make you read a paper that'll also give you examples. I'll make you do examples. The next homework, by the way, is going to be doing a simple problem in progression, regression, and plan space way. Just trace it by hand with the search tree, so that you know actually what is happening. And then, of course, there are actually search algorithms that do this. Okay. So here is a simple example that we'll try to walk you through. So apparently, I'm still doing the old problem, apparently. So not clear B, hand empty. And so one thing, actually, I'm not sure why I put both actions, but imagine we are in the sort of in the middle of the plan, I guess. So in here, let's look at, actually, let me look at first. Let me show you the algorithm, and let me show you the algorithm and then show the example. Algorithm looks very kind of, complicated enough. The nice thing about progression and regression is that you can think of the current state in terms of prefix or suffix. For the prefix, you can completely remember the prefix by the state that is true after the prefix. For the suffix, you can completely remember the suffix by thinking of the state that would need to be true such that the entire suffix can be executed. And in search, underneath a prefix branch, the prefix will never change. Underneath a suffix branch, the suffix will never change. In this kind of planning, essentially, it's just a bunch of actions with precedence constraints between them and causal link constraints. That's it. A plan is just a sequence, a set of constraints on actions. It's a partial ordering on actions. Right? And a partial order sometimes might correspond to a total order, or any total order that is consistent with the partial order is a correct plan. So for example, if you made the partial ordered plan for the one-way rocket, it would look like start, load A, load B in parallel. That means I don't care about their ordering. Both of them come before fly, then unload A, unload B in parallel, end. Right? There are 4 different linearizations of this plan. Because it's a partially ordered plan, there are 4 different linearizations of this plan. All of them are correct. Right? This is the way you think about planning now. You think of plan as just a constraint set on the action sequences. Okay, so that's why, the partial order plan is this crazy tuple, actions, ordering relations, links, and there is these 2 things called open conditions and unsafe links. And the open conditions and unsafe links can be derived, actually. Okay, so what is the actions is just of the actions. In fact, the one thing I want to mention is because the same action can be done more than once in the plan. Do you see this? You can do the same action more than once in the plan. Right? And every time that action comes, you need to give it a different step name. So actually what you do is actions are really a set of action steps. The steps correspond to individual real actions. So S1, S7, S9 can all correspond to A1. But S1 is the step 1. You see what I'm saying? So you think in terms of plan actions as SI and the action name. But, so there is the actions, and the ordering is always between steps, not between the real actions, but the steps. And if you're ordering the steps, then you're ordering basically the step is corresponding to A1. S1 is A1, S7 is A5. So S1 comes before A1. S7 means this A1 is going to come before A7, this particular instance of A1. Do you see what I'm saying? There can be multiple instances of the same action in the plan. Okay, and The action ordering essentially is saying SI before SJ. This is a precedence relations, not contiguity relations. They're not star. I will talk about star in a minute, but they're not star. Okay. And then links are causal links. Essentially, it says some step SI. I'll for now assume there are no conditional effects to make life simple. Simple, normal propositional strips. Okay. So SI gives P to SJ. That's the kind of conditional effect, causal links. And then if I give this AOL, then I can derive easily open conditions and unsafe links. Those are essentially the flaws in the plan. They are the derived constraints. Open conditions are conditions which are preconditions of some steps for whom there is no causal link. They are not at the consumer end of any causal link that has already been done. That means you're still hanging around, nobody is supporting you. Right? Unsafe links, on the other hand, is you do have a causal link supporting you. You are S7. I mean, so you are like condition P for S7, and S5 is supporting condition P, but S9 can potentially come in between and delete condition P. That's why it's unsafe. Right? So these OC and UL can be thought of as flaws in the plan. And they initialize the plan by saying S0, which will have as effects all the initial state conditions, S infinity, whose preconditions will be all the goal state conditions. And you will put one actual ordering relation saying S0 before S infinity. That's it. That's the null plan. And then, of course, that will have open conditions, right? Because the S infinity has a bunch of conditions which are not supported. They're not at the end of any causal links. So those would be listed in the open conditions. So the null plan essentially has S0, S infinity, no links, open conditions corresponding to the preconditions, basically the top level goals. What's the termination condition? Termination condition is if you have a plan that has no open conditions and no unsafe links, you're done. That's it. That means a flawless plan. And so what is the search? Search is pick a flaw, make it go away. So if you have an open condition, you'll pick it, take some step and make sure that that step gives that condition. There are two ways you can do it. One is that the step that you're using already exists in the plan. It's called simple establishment. The other is you take a new action from somewhere, from the library, put a step name to it, put it into the plan and say, you now give P to this condition. When you do the step addition, you have to actually introduce this new step and put an action ordering between that step and where the condition is being used. Then the open condition can be removed because now it's being supported. So if you remove all the open conditions this way, are we done? No. What happens is when you put this as new step, it has preconditions. Those are new open conditions. So the list of open conditions changes non-monotonically. Do you people understand this? This is like one of the most important things about planning. You can make number of goals. If somebody says, oh, the difficulty about planning is there can be too many goals, that's bogus. If you say you have G1 to Gn as the goals, oh, there's too many goals, I will make up a new action called Tom's action, which has as precondition G1 to Gn, and effect Tom is done. And I'll just say, Tom, just be done. One condition, one goal. You see what I'm saying? that in trying to achieve that one goal, you put in this storm action, which will then bring back all the G1 to Gn. So open condition list keeps increasing and reducing and increasing and reducing. Similarly, unsafe links, when you introduce new steps, their orderings might be too unconstrained, and so they get onto each other's way. And so you would have to either promote or demote that action so that the unsafe link will go away. And as you keep doing this, at some point of time, you might reach a partial plan which has no open conditions, no unsafe links. Then before it changes its mind, it'll say, I'm done. This is the plan. The example is here. I'll show it to you, and then you get to go home. Very simple example. And I'll also give you a video that you can watch where I'm slowly walking you through it. Okay. But this is like simple. It's actually very simple. It just looks weird. There's so much. It's an extremely simple example, right? Goals are P and Q. Action is very simple action. A1 takes M, gives P and not N. And A2 takes N and gives Q. Right? And the initial state is M and N, goal state is P and Q. So I'm going to just mark here. I start with the simple null plan here, I before G. And then G has these preconditions, Q at G and P at G. Those are the open conditions. Then I have to pick one of the flaws. Let's say I'll pick Q at G. So then I doesn't have Q because I basically has M and N. Right? So I will introduce A2 because A2 gives Q. I will give it a step name. Basically, I will say S1, A2. I'll just wrote A2, but I should say S1, A2. And A2 is giving Q to G. So now G is no longer an open condition. But then because I took A2, then A2 needs N before it. N at A2 is a precondition. So now this is my plan. It has just one open condition N at A2 and another open condition P at G because that's still there. And then I put A1 to give P. Now I have an actually partially ordered plan. A1 and A2 are kind of unordered. A2 is giving Q, A1 is giving P to G. Everything is nice except that A1 removes N. A1 removes N. That's still okay. So A2 requires N at A2. Right? Initial state does have N. So I gives N. But then at this point, A1 can come between I and A2 and remove N. So I need to put A1 either before initial state or after A2. Nothing can come before initial state. That's like B before Big Bang. So that branch is killed right away because there is circularity in the ordering. And so the only branch that survives is A2 comes before A1. At this point, I will argue you're done. There are no open conditions. There are no unsafe links. You see what I'm saying? Stare at this. This is what you actually do in terms of the flexibility here is everything can be individually fixed. You can fix at a condition level. In progression and regression, you fix it by adding an action and extending the suffix or prefix. Okay. And then I just want to show you this slide, and then you can really go. Yeah. Okay. Because I'm going to make you read this before coming to the class. Yeah. I would actually argue that there are, even though I acted as if there is progression, there is regression, there is plan space, I can combine all of them into one single search. You can see how already I can combine progression and regression. That's bidirectional search. You extend prefix this way, extend suffix this way. When the suffix state is already present in the prefix state, you're done. That's bidirectional search. I now can throw in the plan space too. So what I call this causal link thing is called plan space. refinement. In general, you will assume that the ordering relations that are introduced by progression are contiguity ordering between the prefix actions. Regression introduces contiguity relations, cementing them in the backward side. The planning guys are they're like rubber band precedences. Additional actions can be between without violating the precedents. So you combine these, there is actually this paper that I'll make you read, mostly because I wrote it, called Refinement Planning, which essentially combines progression, regression, plan space. Lovely, beautiful, unified view. It doesn't work any better than any of the individual ones, but since I made it, I make you read. It gives you a unified view. Some of the times, unified views don't necessarily improve efficiency, but it actually makes you realize that it's just three different, I made it look as if, in fact, it so happens that you can write sorting algorithms that combine all sorting algorithms. You didn't write them that way. You tended to either make the prefix sorted, suffix sorted, or bubble sort. You can do prefix, suffix, and bubble in the middle. That's basically what I'm saying here. We will end here. Thank you for your extra 5 minutes. And I will send you things to read before coming to the class so that you will understand plan space as well as this stuff. And then we'll talk about heuristics next class.